All right, we're going to continue our exploration of mechanisms in chapter 21 by doing a chromic acid oxidation of phenol. A lot of reactions of phenol, huh? We have to make a chromate ester every time we do a chromic acid oxidation. That's the same every time. See how concise we can make this. 3 colors at least. Red first. Blue second. Purple third. We got to activate the chromium to attack by an alcohol. That's step 1. You got to do that with a strong acid. Step 2, as implied by my description, attack using the alcohol, which is not a good nucleophile. That's why we had to activate. A lot of you think you can do it without activating. The results were you lost a point for not protonating first. It happened to at least 2 of you, maybe 3 on the last exam. And then you're going to generate an oxonium on the phenol oxygen. And keeping in mind, you just made a sulfate ion that's going to neutralize that oxonium. You can't neutralize it until it's an oxonium because it's not a strong enough acid. The blue arrows made an oxonium. The purple arrows are going to neutralize it. And you are almost all the way to your chromate ester. You got your phenol. You've got your O. You got your chromium. Still has a double bond on top. There's an OH on the bottom, to the right. There's an OH underneath. There's an OH to the left. Time to make a chromate ester. I don't know, maybe I can shrink this arrow a little bit. Look at you. Worried about space, that's all. Acid catalyzed dehydration time. Catalyzed dehydration. You're gonna need an acid catalyst. Purpose of the catalyst. Make one of the OHs a better leaving group. Pick one of the 3. Protonate it to make it a better leaving group. The base you just generated. We'll now do your elimination in baby blue. You've made a good leaving group. Here's your beta elimination. Grab a beta H, make a pi, leaving group leaves from the alpha position. You want Greek letters? I haven't talked about it this way in a long time. That's the same as beta elimination in chapter 6. Okay. Beautiful. We made a chromate ester. What do chromate esters always do? There's a reason it's called chromic acid oxidation, everybody. It's gonna, I want to hear oxidation. That's what I want to hear. That's it. Good answer. Sorry. Now, normally, you'd grab an H from here. I'm going to draw this. If I did this on a test, though, I'd get a -1 on there and an OV comment. Normally, you take an H from here, right? There's no H there. Don't pretend there is. But isn't there a way to make chromium leave like this? And then, let's see. There's got to be something going on in the pair position eventually, right? How the heck does that O get there? If there was a carbocation on the carbon, water could attack it. A second resonance arrow here will generate a carbocation and do the oxidation for us. Isn't that sweet? That's a little twist on our first oxidation. All because we didn't have an H in our normal spot. Resonance took care of it. So oxidation number 1 is complete here. You got your carbonyl. Double here, cation here. In fact, what did I say is going to happen to the carbocation? I think I said it already. Attacked by what? What nucleophile? The OH in water. Dudes and ladies. Can't we do a second step and go straight to the oxonium that results from the cation? Have the cation in your mind because that's how the O got there. But here's your water. After you make that cation, hit it up. Oh man, we got purple still in spare here. I didn't change the water. Didn't change the water, did I? It's still water. But you're going to generate an oxonium, aren't you? What do you think step 3 is? Same as the purple step 3 that we started the day with. Sulfate ion, which you've got available at all times. Here it is. OSO3H lone pair minus purple. It's a little tight there, isn't it? Can I move the whole thing? Yes, I can. Purple. You got another phenol. Ah, blue. Big finish. Yeah. Hi. What happened there? I went to the previous page. Just had a heart attack there for a second. It's all gone. Okay. All right. Now it's straight up traditional oxidation number 2, chromic acid oxidation. That's a normal alcohol. It's got an H in the spot I need it too. So let's not mince words. I'm gonna, okay. I need space at the top, I think. Maybe. Yeah, lots of space. I need chromic acid number 2. Wow. Thought I had the pen on. Now I do. Chromic acid number 2. Sulfuric acid number 2. Protonate first. You thought this mechanism was important before. Now it's worth twice as many points. I'm going for baby blue next. And that H is going to be drawn off of here. Sorry. Keep getting these great ideas after the fact. Sulfate ion you just made here. Gonna grab it. Purple. And what you got? What you got? Yeah, chromate ester number 2 almost. It's the hydrate. Still have a double bond on top. Got an OH to the left. Got an OH underneath. Got an OH to the right. Time to make chromate ester number 2. Same way we make chromate ester number 1. Be nice if we can see everything on the same screen. Here it is. We're going from here to here. Let's see. You want the alpha and beta deal again? Why not? Beta, alpha, leaving group has to be created first. I got a keyboard randomly. And I'm going to eventually need the conjugate base of that species. And step one is to protonate this, make it a better leaving group. Step two is to do the elimination. Grab beta H, baby blue. Make sigma into pi. Leaving group leaves. Chromate ester number 2, right here. Chromate ester number 2. Got a blue O. And this is a very traditional chromic acid oxidation. In that, there's an H on that position that we need it on. You can use water to grab that H or sulfate ion. I'm not that picky. Traditionally, we've been using water. Sulfate's okay too. And you made a very special species called, oh, I have my arrow going the wrong way, don't I? It doesn't go there. Looking ahead a little too far. We're going there. Yeah. So we got a big old loop around going to the middle. And the last part's easy. We can fit it in underneath here. It's not a biggie. Hey, that's aluminum hydride there. Every time you see Al with 4 H's and a minus charge, you do this first. Make a hydride. What the heck can I do with hydride? Normally I tack a carbonyl, right? Please don't do that. None of the products has an H on the carbon that used to be a carbonyl carbon. Don't do that. Products have H on oxygen, each oxygen. This is the only time you're ever going to see H minus attack the oxygen. This is it. It's actually attacking the negative atom. Doesn't make sense. But if you paid careful attention at the start of the day and you realize you're going to be making an aromatic molecule, this is aromatic. This is not. You can't resonate in a circle here. So yeah, you can do weird things if you can make something aromatic. And I want to use magic words that we've seen before. Conjugate addition. Usually you think 1,4, right? How about 1,8? Not the first time we've seen that either. We had an activity before the exam. There was a 1,8 addition. If I attack here, you've just made the oxygen position number 1 because you attacked it. Resonate past 2 and 3, past 4 and 5, to 6, and then 7 and 8. Here's the numbering for the mechanism. 1, 2, 3, 4. Okay, it's not 1,8, it's 1,6. I lied because I can't count. It's a 1,6 addition. We even put that over the arrow here. 1,6 addition. One, 6. Okay, and now you got your H down there on your O. Double bond, O minus. My goodness, that looks a lot like this product here. How do you get that H on there? Step 1 is over, everybody. That's just a good old acid-base reaction in step 2. Take it from the I forgot to edit HOH, by the way. My mistake. That should have been HCl all along. I copy pasted HOH. I was in a hurry. I was going to edit it. Forgot. HCl is better. So fix that HOH, make it HCl, and oh man, that's just coming too close to other stuff there. There we go. HCl, better acid. And you took something that was a p-quinone, paraquinone, and you made it something into something called dihydro p-quinone. Dihydroparaquinone. Quinones are very important in biochemistry. You're going to read about them in the textbook. A lot of redox happens inside of your body because quinones are there to facilitate. They're going between their oxidized state, quinone, to their reduced state, the dihydroparaquinone. And things like NAD plus and NADH are involved as well. We have a question.
Yeah, I don't know why that structure is there. Like,
Which structure? This bottom right random structure just showing up out of nowhere? Yeah, I should have gone straight up there. That's a good question. I think it's because I changed my mind and did the deprotonation. And then I forgot I had the start of a drawing there. It's fun to figure out where your mind makes mistakes and then retrace after that. There we go. And there's the big picture, and I don't think we have time for an activity 7. Trying to save here. Stop the video though.